Hey you guys, welcome back to the channel PHYSICSSIRJEE. And as you already know that I'm going to launch an online course for both JEE 2023, which will be a crash course, and JEE 2024, which as demanded by the students, will be a full-length lecture plus problems. And in both the courses, there will be live doubt sessions and also the DPP solving. Okay. So I've already provided you the sample JEE 2023 course video, right? And then the poll I said I will be taking up a demo lecture for the kinematics on chasing problems. So this is one of the multiple lectures that you would be having it as part of the online course. Okay, so this will help students to ensure to take an informed decision whether to buy or go for the course or not. Okay, so before we move further, I would request you to like, share, and subscribe to the channel so that by the end of it, you don't forget. Also, there is a launch of a Hindi channel to give students who are comfortable in Hindi mixed with English teaching, right? So you can go ahead and check that particular channel. The link of the channel is in the I button above or the description below. And regarding this video, I repeat, it's not the complete chasing problems theory lecture, theory plus problems. It is cut from one of the full length lectures of the kinematics. So students who will be taking up the course will be able to enjoy from the basic level to the advanced level theory and problem solving from JEE mains and JEE advanced and ultimately for the Olympiad. So all of this in the nutshell will be part of the full length lectures. So not all problems are included in demo. So as a thumbnail suggests, there will be chasing problems. So you would expect all types of chasing problems and relative motion questions. Yes, that they will be there in the full length lectures, but this would be having only a part of it. Okay, so if you just provide 500 likes to this particular video, then I'll upload the live doubt session demo for this chasing problem lecture. So in our course, after certain lectures, there will be one live doubt solving. The doubt solving will be from the classwork, that is the lecture itself, right? Some students, when they are going through the lecture, they will have some doubts. So I would like to clarify those doubts in the live session, and also the DPP sheets, the worksheets, tests that will be conducted, all those things, students will definitely have some doubts about. So we'll have consistent and sequential doubt solving sessions. So I would like to upload a doubt solving demo also so that you will have a basic idea of how the course is going to be. Okay, and announcements about the launch of the course, it's coming up within few days time. I'm taking up some time to prepare the lectures of first few chapters, and then also the platform is getting ready on which the lectures will be delivered and the course will be delivered, both 2023 course and 2024 course, and the price for that particular courses will be announced very soon, so be connected with me. Also, students watching this particular video till the end will find some concepts and explanations not given in the books. So I would urge you students to actually go through it till the end. Also, pause the video at appropriate places because this is going to be a slightly lengthy video, as it's a full length lecture consisting of some beautiful problems, some of them famous ones with different way of attacking, and some of them very new questions that you might not have seen anywhere. So pause the video if you are a student and then read the question and then go ahead with the solution that I'm going to give in the lecture. So since this is cut from a bigger part of a lecture, it starts off with a three ant problem, the famous one where the chasing takes place, each ant trying to go towards one another. Okay, right. But the only difference is that the problem has a small change of not constant speeds, but constant acceleration. So already the first part of the problem was solved before. So we'll continue from the second part. So you want the first part, you can take a snapshot of the initial slide that I'm going to now show and then solve it. And then the second part becomes very easy to understand. I hope you would go ahead and enjoy the lecture. Pending. So this was the last problem that we discussed in the miscellaneous problems section. So and we'll continue the miscellaneous problems. Okay. So the first question was, after what time the ants actually are going, ants or the programmed robots are going to meet. We have seen that. Okay. And the second question, which was the homework, we'll now see the solution of that. After what time right? I forgot to write the word time there. Okay, so let me fill it up. After what time will the area formed by the triangle of the robots be half the initial? Robots be half the initial. Okay, so right, T is silent in robots. Okay, so I think we go to the solution of the first question. You will get a hint of what to do. I think in the second question, right? See, just borrow this integral. Let's shamelessly copy it. Okay, right? And then change the integration, right? So the thing is, the lower integral will still be the same. At t equal to 0, it would be at s. Okay, and the upper part, which is let's say half area part, maybe some t prime, the time duration. If I'm looking at half area of the triangle, then I should be looking at a side length of s by root 2. I think that should solve the purpose for the second question. So this would be s into 1 minus 1 by root 2 is equal to 3 by 4 a naught into t prime square. Okay, right. So just like last time, the value of t prime would be a square root of, just exactly the same as the last one, but you would just end up having the replacement for that s. So this would be 4 times divided by 3 a naught with s replaced with s into 1 minus 1 by root. So this is your answer for half the area. So this was the important part, how we integrate it. Okay. Let's go to the next one. So next one is a very famous question, appeared in one of the exams in the past, and you could see this in IRODOV problem book also, right? So I like to call it as, this is just a name I give so that we can recognize it in the future also. I call it as Tom and Jerry problem. Okay, right? It's one of the famous chasing problems that we usually do. Okay, so you have a line on which a mouse, or Jerry is the mouse. Okay, so this is the place where Jerry is, right? The mouse is, and at a line which is perpendicular to that white line, and at a distance of d, at a distance of d, at a distance of d from there, Tom, or the cat, is waiting to catch up with Jerry. So just like the program robots in the previous problem, you could visualize that the cat is always willing to chase the mouse, which means at any later instance, when the Jerry actually only supposed to move along this line. So Jerry is only supposed to move along this line, okay, along that this particular straight line, and Tom is supposed to always follow it, such that at every arbitrary instant, the velocity vector of Tom at any instant, if you um, aim it, it should be always aimed at the position of Jerry, similar to A aiming B and B aiming C in the last problem. So at any arbitrary position, if this was the curve followed by the Tom and it is right now here, then the velocity vector of Tom is this way, and if you extend it in a dotted line manner, that would be the position of Jerry. This would be the Tom at a later stage. This is it, and Jerry is always moving towards right with a speed u, and Tom's speed is always v. Okay, right. So this is the condition. So this white line is Jerry's path. Right. The blue line is the Tom's path, like this. Okay. So the conditioning is this way: V bar always points towards position of cherry or the mouse. Okay. If V is greater than U in magnitude, then after what time from the start? After what time from the start will Tom catch Jerry? This is the question. So another one of the famous chasing problems. Okay. Okay. Right. So just like yesterday's spring idea that I said, there is a compression and how you write the velocity vectors. So at any arbitrary instant, if this was the position of that Tom, imagine there is a hypothetical spring like this at that particular place, and the velocity vector of Tom, which is in this direction, velocity vector of the Tom, which is in this direction, and velocity vector of Jerry, which is in this direction, are managing to ensure that this particular distance between them, which I'll mark as some x, okay, so distance is x, okay, so that x is reducing because of, now if I extend this dotted line in this manner and argue that this some angle is theta, right, you could see that angle theta. If I draw the spring on the sidelines just the way I explained in the previous problem, a hypothetical spring which is getting compressed, it is the complete V and the component of U, which is U cos theta that you have. These two are responsible for either reduction or increase in x. Okay, right. So if I write dx by dt, this is nothing but rate of change of x, or simply rate of increase of x. If I want to call it as rate of decrease of x, I need to put a minus sign. So let's look at it as a increase only. I know we are supposed to reduce it, but let's talk about it as a increase only. Only way why I'm doing this way is, in the previous problem, we did it in the form of a decrease. You could see this one that we did last problem, we called it as a decrease. So the job was to compress. So any job which is a compression, I put it as a positive sign, and any job which is compression here, I put it as positive sign. So just wanted to do something different here, right? That's why I'm taking it as a extension job now. Okay, so dx by dt would be positive if it is extending and negative if it is compressing. So this should be equal to, okay, now let's look at V, what job V is doing. Is it compressing or extending? And look at this. If V was given a choice, then it would compress this. That means this should support this with a minus sign. Okay, so this would be a minus V, and then plus your U cos theta. Okay, so again, like last time, I note that this one's job is to compress, and this one's job, U cos theta, can you see? U cos theta is trying to expand the spring. Okay, so that's why these two share opposite sign, even though they share same direction. I told you yesterday, this is not based on the direction, this is more based on the type of job. This is a scalar equation, not a vector equation. Rate of change of separation, that is we are talking about, it's a scalar. So this job is to expand. If I had on the left hand side written minus dx by dt, then this would become plus and this would become minus. It's mathematically the same thing that we are looking at. Okay, right. So when you rearrange like last time and write minus dx this time is equal to v, and you have a u cos theta. I have to take dt on this side and try to perform the integration. So this integral, and this integral with a obvious minus sign in between. But there is a small problem here. Okay, so what is the first value of x? Let's look at the first separation distance. The first separation would be this distance itself. Can you see this distance? This would be the first separation, which he gave it as d. Okay, so that would be my first limiting substitution. This would be d. And the last one, that when they meet, whenever they meet, is 0. And the first instant, and this would be the last instant. This would be first instant. This would be last instant. Okay, now the left hand side is d itself because there is a minus sign. This would be, because v is a constant, it comes out and you would get a vt, no issue with that. Minus u comes out, but cos theta can't be integrated over dt. Remember, this is dt. Had it been d theta, I would have done something about it. Okay, so this one stays there. Okay, so the problem is this is an unknown quantity. Okay, right. So we can't go further. So we'll take a break here and go and investigate how you can get that cos theta in any other form. Okay. Now, if I mark some axis in this direction, okay, let me mark some axis here. This way I'll take x-axis, and this way I'll take y-axis. Okay, right. So, and this x and this yellow x have nothing to do with each other. Remember, this x has been used as a, I could have used s also, right? So I know there could be some confusion for you for this x and this x. This is a different purpose, and this is x coordinate I'm talking about. Now, if someone wants to have some relation in terms of theta, especially cos theta, they could say that if this velocity vector v can be brought here. Okay, let me bring that v to this place. Okay, and that same angle that I have here, theta, can be expressed even here, right? So maybe I can think of another equation that will portray the v cos theta's properties, v cos theta's properties. For that, I need to look at only the x direction motion of the cat and x direction motion of the mouse. Now, how did I get this idea? The idea is got because I couldn't go further in this separation equation. Remember, the separation equation is a scalar equation, has nothing to do with x or y. I realized that after writing that expression, I can't integrate this further, unlike the previous problem of robos. Then I went back as a common sense to investigate how can I write another equation to eliminate cos theta. I quickly realized that cos theta is another component of the velocity vector in x direction. So that gives me an idea that I have to write one more equation of motion in x direction. So with that idea, I go forward. In x direction of motion, in x direction of motion. Okay, right. Both cat and mouse should travel same distance, right? Y direction wise, they don't travel the same distance. But you see, cat starts here, and if it ends meeting up mouse here, the x distance traveled by cat, which would be projected onto x-axis like this, can you all see this? Should be equal to the x distance traveled by mouse, because initially both of them have same x coordinate. So the distance traveled along x-axis for both of them should be same. For catching up, delta x of cat should be equal to delta x of mouse, or you can just write Tom and Jerry. So what is delta x of cat? Delta x of cat would be simply integral of v cos theta dt, because its x component is 0 to capital T. And this should be simply, remember, mouse is moving along x-axis with a constant velocity. Therefore, this should be u into t. Okay, so this should give you
that integral of 0 to capital T cos theta dt, I brought V out and I'm sending it on to the other side, is ut by V. Can you see we achieved our goal of estimating this cos theta? So this unknown has been estimated here using some common sense. So I'll borrow this equation all over again and substitute that expression. Okay, right. So upon substitution, that expression simply becomes d is equal to vt minus u times of, I'll substitute this, ut divided by v. I just substituted this one here. Can you see ut divided by v? Okay. So just to highlight that substitution, maybe I can use the same color. Okay, so I just substituted ut divided by v. So rearranging and getting the value of time, the value of t will be equal to d into v divided by v square minus u square. V square minus u square. Okay, so this would be your expression for the time taken, and tells you something very simple, that v has to be greater than u for this time to be a plausible time or a compatible answer. Okay, so that's why in the original question, if you drag it down, you would see that he has mentioned that v has to be more than u. So if this condition was not given, you could conclude like most of the Tom and Jerry cartoons, right? The Tom is not going to catch Jerry. Okay, so this physically is very important. The cat has to be faster than the mouse so that it can dream of even catching it after this much time. So it's slightly difficult question for those students, especially doing it for the first time. You don't expect them to get this entire discussion in one go. So I repeat, we did it in two parts. First part is the separation equation that we wrote. This has nothing to do with any direction. This equation looks at how this gap between the two is reducing. At the end of it, we got a roadblock here. We couldn't go. This was like a dead end, right? We couldn't integrate. And then we tried to go to the x direction of motion because I saw a cos theta here. Remember, if I had seen a sin theta here, I would have gone into y direction. Okay, so this was an afterthought. And then I eliminated that integral without integrating it. I just eliminated it and get the value of time. Okay, right. So to check how much you have understood, I would like you to attempt a homework question on a similar problem, but slightly modified. We all know that if v is less than u, then cat won't reach the mouse. And if v is greater than u, we saw it reaches it with after some time. Let's do the critical state. When v is equal to u, that's your homework. Same problem without any change. So this is the Tom, and initial position of Jerry is here. Question is, repeat the above problem if value of v magnitude wise should be equal to u. So u is this velocity and v always aims at u. So this would be magnitude wise, it seems they are the same. So you should say t always aims at j. How do you write it in a vector equation form? So just let's make a note. This is an interesting way of reading the situation, a vector way. So at this particular point, if this is your position t and this is your position j, what he's trying to tell you is that the velocity vector of v is, can I say, parallel to the position of j with respect to t? Position vector of j with respect to t. With respect to t, right? This vector and the velocity vector of the cat are parallel to each other. Okay, so if someone wants to just put you off in an exam, instead of writing all these English statements, he can write a vectorial setup saying that the velocity unit vector is equal to the position unit vector. So How do you write this entire thing in position vector? Is it tj bar or jt bar? If I want to join a vector from here to here, j with respect to t, you should write it as tj bar or jt bar. It should be tj bar. So what he is saying is tj bar is parallel to v bar. So, or simply the tj cap and v cap are equal to each other. Not just they are equal, in this problem even the speeds are equal. So the question is, what would be the distance between Tom and Jerry after long time? After a long time. Okay, we know it can't catch it because v is right. That long time will be infinite time. In that long time, we expect that Tom to reach this line, but Jerry will be ahead. And since both of them are traveling with same velocities, they'll maintain a gap, and that maintained gap will be throughout the same. So he wants that gap. What would be that gap after a long time? He wants that in terms of obviously the original value, original gap between them, which is given to you. Okay, so this gap, like in the last question, is d. So in terms of d, you need to estimate. Right. So that's the Tom and Jerry situation. Okay, let's take up another question of chasing. So we are now looking at a diagram in vertical plane. A diagram in a vertical plane. Imagine there is a floor. This is the direction of acceleration due to gravity. Okay, right. On the floor there is a drop of honey. So this is a drop of honey. There's a vertical line joining the drop, and at a height d, from the drop of honey, a honeybee is moving horizontally. So this distance is given as d. A honeybee is moving like this along this line. Okay, right. So let's say the drop point is point O, and exactly the topmost point where we marked the distance d is, let's say, P. Honeybee is moving along this line horizontally, right, towards that point P. When the honeybee is exactly above the drop, with its eyes it sees the drop. Okay, and then from that point onwards it starts trying to get to the drop. Okay, right. What cannot happen is that this honeybee cannot actually stop here immediately and come down. In real life, what happens is by the time it comes here, it has some inertia of motion. So it will continue, but it wants to turn itself and then come to this point. So it's because there is already some velocity. So assume that initial velocity of the honeybee is u till p. Travels with a constant velocity u till point P. When at P, it notices the drop. And using its wings, which can provide a maximum magnitude of acceleration of net value a naught, including its weight on everything taken. Net acceleration that the honeybee can have is a naught. Using its wings, it tries to change its direction and reach the honey drop in shortest possible time. Okay, this find that time, that's the question. Okay, I hope you understood. It's difficult explaining this question, but I think you understood the wording of the question. So honeybee was nicely traveling, it singing till here. Suddenly it watches the drop. It can't come down because abruptly stopping and coming down requires infinite acceleration. What is the maximum it can be provided with? A naught. So instead it has to slow down, take a turn or curve and come like this. We don't know what kind of curve this is, but it should ensure that a naught cannot exceed the value of this thing. Okay, so it has to curve and then it will take some time before it can actually reach what is the maximum minimum possible time. Okay, I'll just give you half a minute to think over this. Okay, in that value of a naught, this g is included. So maybe for this particular problem, you don't require this g because g's contribution is included in this e naught. He said net value, so don't worry about g in this problem. Okay. That you can have is by choosing an appropriate frame of reference. Okay, right. So because by choosing an appropriate frame of reference, you would be able to simplify the way in which you can view the motion. Okay, so what I will do is once it reaches this point P, from that point, after honeybee reaches P, choose a reference frame moving with a constant velocity of that u in rightward direction. Okay. Note that this is an inertial frame. What is an inertial frame? Inertial frame is a frame in which the acceleration calculation is always correct. Okay, right. So even though it has velocity, it's a constant velocity. So even in this frame, the acceleration has to be a naught. Remember, there won't be any change, but the velocities could change. The reason why I'm telling you this is that in that yellow colored frame which is moving like this with you, let's say the observer is on this frame of reference. Okay, so he would think that the honeybee is actually starting from rest. So he would say the value of u relative initially for the honeybee is 0, whereas he would see the drop actually moving towards left, right? For any observer who moves towards right, he sees a drop which is actually at rest to be moving towards left with a speed u. I think you will all agree with that, va bar minus vb bar. So he would argue that this velocity is u and it's constant, okay, right? Because the reference frame is a constant frame. Now it becomes a simple problem. A particle starting at rest, okay, a particle starting at rest has to chase this particle in shortest duration with a with a highest possible acceleration of a naught. So in this reference frame, right, that has to move along a straight line to catch up that position in a future position here. So this has to travel to some position here, and this has to travel along a straight line with a constant acceleration and reach this position. Why straight line? Because it has to be doing so in a least possible time. So we remove this problem of initial velocity. Once the initial velocity is 0, a particle which is accelerating has to move to a point, right, in a shortest duration. It has to do so in a straight line. Actual path is not straight line. In this reference frame, it will look like a straight line. Okay, so which makes it easier problem to solve. So the future position should be such that the time duration for this motion of the honeybee, okay, so this is honeybee moving, and this motion of the honey itself, this should happen in same time. So that time, let's say, is t. We all know in constant acceleration motion this should be half a naught t square, okay, and this distance that you marked here should be, I think, ut, because it's a constant motion. Okay, and what was this gap that you were given? I think this gap was initially given as d. This should form a nice right angle triangle. So equating them, you would say value of d square plus that ut that you wrote in the diagram whole square should be equal to that half a naught t square hypotenuse, but you should say whole square. So this would be a quadratic in t square which we can solve for. We'll use minus b plus or minus root of 4ac, root of b square minus 4ac and all that. Okay, right. So now let's make a note. What would be the actual path? The path seen by a guy moving with a constant velocity looks like a straight line making a certain angle with the initial velocity. Then I think we all know that if I get to a ground frame and watch this, right, you have a u like this and a constant acceleration this way. We all know that path is a parabolic path. So the actual path with respect to rest frame or ground frame would be due to the aspect that there was a initial velocity u like this, which is a value, and there was a acceleration vector. Remember, ground frame and that moving frame measure same acceleration because both are inertial frames. So this acceleration should be true in both the frames. Whatever a naught I had, the same a naught I should have here. Maybe I can mark it in the same blue color that I wrote. These two blue lines are parallel to each other. So whenever a velocity vector and acceleration vector make an angle other than 0 degrees and 180 degrees, what is the path that we have seen? This is like an example of a projectile motion. So the actual path is a parabola. Maybe you can think of it like this. So if this was the honey drop, the path would be something of this sort. So it was supposed to move like this, but it will curve like this and then reach like this. So this would be the parabola I am talking about. But that would be very hard to see directly. So we had to change the frame to a relative frame of this observer to estimate that. And after seeing that, now things become very easy. Okay, I didn't solve it. Okay, I'm a bit lazy here. Value of t comes out to be some square root of something. So I'm leaving it for you. Okay. Let's go to the next one. Let's try to see another relative motion question in Riverman problems. Okay, right. So we are going back to the Riverman problems under the miscellaneous section. So the age-old top view of the Riverman situations. So we're looking at the top view of the diagram, and same, we have one person starting at O, exact opposite point on the bank, let's say is A. This is A, okay, and the gap is mentioned to us. This gap is D, right? That's also given. The flow of the river towards right, is having a value U. Okay, so velocity of the boat, I told you examiner may use a language that's comfortable to him. So whenever you see in a text, you may not see it in my classwork because I don't like writing it like this. So VBR I will write. So if they put a comma, it's like velocity of boat with respect to river. That's what it is. So I'm using that notation also so that you're getting familiar with this. The value of that is given as V itself. Okay, right. Let me write a small v. It doesn't get mixed up. So the boat or the person who is going across the stream can go at a speed of v with respect to the river. Boat starts at O. The information is given like this. Boat starts at O and always aims at A. So unlike all our Riverman problems where once the person chooses an aim, he never changes it during our motion there. But in this problem, it's slightly different. So what actually happens in this question is that initially the person will aim towards A like this, but he gets drifted to a new position here. Then he changes his aiming direction towards always wherever he goes at that position, the velocity vector should be aiming towards the position A. Okay, this is a very bad diagram I have drawn, but that's how it should be. Okay, so speed is this constant, right? So this value will be a constant in magnitude but changing direction always. Okay, so that's the idea. So let me erase that parts in the diagram. So this is like your Tom and Jerry thing only, where always it will be aiming towards that. Given the value of that v is equal to 2 times the value of u, that means twice the speed of the flow. What is the time taken to reach A? What is the time taken to reach A? Okay, right. So it's the question. So I'll just give you half a minute to brood over the problem and then we'll go ahead. let's move ahead. So again, not just one way to solve the problem, but I'll choose something like a reference frame. So you could have actually done similar thing to what we did in case of a Tom and Jerry question by marking a trajectory and then imagining a hypothetical spring between point A, which is fixed, and the point of the boat. Maybe I'll call the boat point as B, right? So that spring will get reduced because of some component of V, and I will be able to integrate and do that, right? So I know that we can do that, but I'll try to choose something nice similar to the honey drop problem. Okay, I'll choose a reference frame. Okay, so let's solve. Because time is frame independent, I'm free to choose any reference frame. Okay, so what I'll do is choose a reference frame to solve the problem, which is a person moving towards right with the speed of the river. So imagine this entire problem is being solved by a person who is actually moving towards right with speed u. So according to this guy's observation, the water will be at rest. The water will be at rest. And since water is at rest, this fellow will see that the boat is always moving with speed v. Remember, a ground observer will not see velocity of boat equal to v. He will see velocity of boat as a resultant of v and u. Okay, right. Whereas a person who is moving with river, he will see velocity of boat as seen by the river, which is v. But not only that, this point A, which is actually at rest with respect to ground observer, what will it happen to this as seen by this guy? I think he would see a rest point to be moving towards left with speed u. So I'll draw all the observation that this fellow will see in this diagram. So this fellow will complain. He sees the point A to be moving towards left actually with a speed u. Okay, right? And he would say the boat which is supposed to move with that yellow colored V would be aiming always like this, with this gap being D. I think by now you would have recognized where we ended up with. I think this is a replica of Tom and Jerry problem. You could see the distance is D, and this will always aim itself. And this is like the jerry, right? This is like a jerry which is moving, and this boat in a frozen water is actually moving to catch up with it. So I'll just borrow the solution from here. So this is equivalent to the Tom and Jerry problem. So after few steps of that solution, you would nicely be able to borrow that the time duration would be, right? You can go back to those pages and directly write it as Vd divided by V square minus U square. And you can check it without this assumption. You can do it in a normal manner. Trust me, you will end up with the same solution. So always you should be vigilant to be able to choose some reference frames. That was the lesson from the last two problems. Don't always look at solving a problem from the ground frame. If any other reference frame can give you a better answer, I wrote wrong spelling for frame. Okay. So any reference frame can give you a better answer or a better insight. We'll choose that. Okay, so that's our solution. And again, as seen in the previous problems, if the boat's power was lesser than this, then it will not be able to catch up. Okay. So V is given as 2u, so maybe you can actually substitute and write the answer. This would be 2d by 3u. Right. Let's move on to the next one. Another practice of Riverman question. So let me mark some important points for this question. A is 1, B is exactly point opposite to the A in the other bank, so I'm not able to draw it straight. Draw it straight. Yeah. So this is your B, and there are two other points which he's marking, one on this side and one on this side. Okay, right? River as usual flows, it seems, towards right with a speed u. Okay. Again, velocity of man with respect to river has a magnitude of same as u. Okay, so the value of man's ability to swim with respect to water is same as the velocity of water. Okay, so the directions could be different. So this is given. Now what happens is man always aims at C while moving but ends at D. The man while swimming always aims at C, but if he aims at C, he would end at C only if river was not flowing. So if a person always aims at C, he will get drifted and move to the right of C. Always there will be a drift because V is equal to U, right? So you expect him to end at some other point other than C. So in this question, he has mentioned that he ends up at D, but ends up at it seems D. That's the importance of the C and D. So if this entire thing is true, you need to give me the value of, find the ratio of the length AB divided by the length BD. What is the value? You need to tell me this. Okay. Again, I'll give you a half a minute to think over how you would approach this problem.
So,
yeah.
Then in the previous question, how can we be sure that it will reach the point like where it's headed always?
I did it using a different frame of reference, no?
But so we are assuming that like it will reach like Jerry, Tom will definitely catch Jerry. So
That
we
is
are
because of
assuming...
this condition. Can you see I changed it? When V is more than U, which is double in this question, and I didn't assume that it will reach. It's clear it will reach here, right? Because it boiled down to becoming a Tom and Jerry problem, right? Once I use this frame of reference, it became this, and this we have already solved, that it becomes a V square minus U square kind of term. So whenever V is more than U, I think it becomes that. So we didn't assume, we went ahead and got a possible answer that it does reach. Okay.
Sir. Sir, in this problem
and
we
one
have
more
doubts.
important thing here, in this new problem, he's not aiming at B, he's aiming at some other point. Okay, so in this problem also, let me make a effort to impress you here. In this problem, if this was not U, listen carefully, if this was not U, right, then there could have been a chance of reaching C, right? That, let's say this is 10U. If the man's capabilities are more powerful than the river's flow, wherever he aims, I think he will try to reach that. But whenever these two are equal to each other, there is no chance. Here I'm pretty sure it won't reach. Okay, right. Now you can continue what you're asking. Someone else was asking something.
So in the previous problem,
yeah,
we took moving frame of reference, no sir.
Perfect.
Then the initial point will also have some U, no sir. Oh, will
That's
have
what
some.
that's what I wrote, no? And one more important thing, is this guy moving always with you?
Yes, sir.
So this point also will always keep moving towards left with you. So that's what I assume.
Sir. Initial point, sir. That V velocity.
So initial points velocity with respect to ground would be what? This is where our previous understanding comes. It should have been a resultant of V and this U, right? Is this the initial points velocity?
Yes, sir.
Now this was initial point's velocity, but when seen by this observer, how will this velocity look like?
Okay, sir.
He will cancel this v, no?
Okay,
And he
sir.
will say, so, and that's the reason why it is called, what is the name of v? We call it velocity of man with respect to river.
River.
I think this fellow is river.
Yes.
I drawn it like a person, but I think I'm doing this with respect to reverse frame of reference.
Yes.
Okay, right. Let me jokingly write that here, okay? Right, so that you appreciate that. So this fellow claims, I am the river. Okay, right. Fine, I'll leave this one as it is so that no. Back to this. So I'll give you 30 seconds more. Think. I didn't give just a second, small information. I think what I asked AB by BD, but I should have told what is the relation between that C, B, and D, right? Just a second. I need to give some information there. Otherwise, you cannot. One more information, please add to the problem that this point C, which he is aiming initially, when line joining A to C is drawn, it makes an angle of 37 degrees with the line AB. So this extra 37 degrees you take. Okay, so that information is given. Without that, you will be not able to uniquely find this number. So this I have added everyone. So I'll change my course. I could solve this using any frame, but since in the previous problem, some students were asking doubt. So I would like to illustrate the next problem using the general observer. That means the ground frame. So you could alternate between the two solutions. Please understand. So my idea is to present all possibilities. So for this problem, I'll use ground observer. I'll just use ground observer. Okay, right. So let's try, so that you get the idea of both the things. I'll draw an arbitrary instant what actually happens. Let me draw all the important lines there. So as one line. So when the person was trying to navigate himself, let's suppose he's moving in this direction at some point. Okay, so what's actually happening here is that his aiming vector is in this direction. Let me draw it in a better manner. So his aiming direction is this way. That's your V. Right, and a U adds to that in this direction. Okay, right. And his velocity vector is in some random direction. Let me write those letters that you have: A, B, C, D. Okay, so this is A, this is B, and what is C? C is in the direction that he aims. So if I were to take that yellow vector and the direction in which he's aiming, extend it, that should be the position of C. Okay, I didn't draw it to scale. So BC, what's the value of BC? BC is equal to, if this was, let's say D, AB is D, then say AB is equal to D. I'll have to eliminate D at the end. That would be D tan 37. I see it as D tan 37. So 3D by 4. Okay, I'm just keeping it like that. And then the value or the position of D is somewhere here. Okay. So the man M is here. Okay, so now this yellow dotted line, if I extend onto the other side also, yellow dotted line, if I extend onto the other side like this, the gap which looks like a spring in my mind. So if C is here and the man M that I wrote, I erased it. So this was M. So if M is here, I imagine a spring between the two, like last time. Okay, and ask you what are the velocities that are trying to change this length x of the spring, or instead of s, x, we'll write s. Okay, so this length s of the spring is being changed by which components of velocity? I would argue, I think I'll get your approval also, that there is a v this way which is trying to reduce the length of that spring, and there is a component of u that you end up having there which also does that job. Okay, right. So how do I mark that angle? Imagine I draw a line. This is getting slightly clumsy, so I'll just zoom it. Okay, so for your easy observation, so stay with me, everyone. So if I draw a line which is parallel to the line that I have been given here, and say that this angle is theta. Can you see that theta? This is theta. Okay, right. What would be this angle, please? This would be 90 minus theta. If you are all okay with this, then I'll move ahead. Can you see this is 90 degrees? This blue line, this red line is 90. So if this is theta, this should be 90 minus theta, because this is one straight line. Okay, so the rest of the angle also should be 90. So this should be 90 minus theta. I've written that. So what is the component of this u along this yellow line, please? That also manages to change the spring length, hypothetical spring length that I am visualizing, right? So I think you all will bet that that value should be u sine theta. Okay, so this s which I have written is increasing or decreasing, that you have to tell. Let's write it in a decreasing form. So minus ds by dt should be equal to, remember minus ds by dt means a decrease in s is due to v trying to reduce that. Can you see v is trying to reduce the spring, whereas u sine theta is trying to expand that spring. So using the idea of the job that we talked about, this should be a positive job of v and a negative job of u sine theta. I hope you're able to appreciate what I am writing here. Okay, right. So this is for the separation equation. Okay, right. And you do the blah blah integral and all that stuff. So minus ds when you integrate should be equal to v into capital T minus u out integration of sine theta dt from 0 to t. When time is 0, what was the s value, please, everyone? What was the s value when time is 0? Here, I think when time was 0, the gap or the spring that you have here was this spring. Can you see? This entire thing was the length, which is AC. Okay, so the first value of the separation limiting wise is AC in the lower limit. What is the upper limit? Upper limit is not 0. After the entire duration is over, it would reach D. So DC is the final length. Okay, so this should reach DC. So this is your equation for separation. Problem with this equation for separation, just like Tom and Jerry problem, is us not being able to solve for this sine theta dt. We are not able to solve for this. So you should look for either x direction motion or y direction motion where this sine theta figures. Okay, where this sine theta figures. If you go in y direction motion, it is v cos theta. So that's not the approved equation that you should write. So maybe I'll look at x direction of motion equation now. Okay, so that's our second analysis. X direction, that is river flow direction equation. What is that? Now let's look at that. I'll borrow those things again. Okay, so at any arbitrary instant, you end up having a v like this. Okay, listen carefully, everyone. There was a u like this. Okay, so this was v and this was u. Now this time what I need is only equations along the blue dotted line. Okay, right. So with that as theta, this as theta, the drift starting from A, listen everyone, it started at A and it reached D. It started at A, it reached D. So along x direction, how much it traveled? It traveled this much. Can I say it traveled BD along x direction? Who is the responsible one for traveling BD distance? I would say U is completely responsible, but V sine theta in reverse direction opposes that motion. So net wise, U minus V sine theta integral over time starting from A gives you BD distance. Okay, so it's slightly difficult, so you need to stay, maybe go back to this video, rewind and see what I was saying. Okay, so in x direction motion, I'll argue u tries to cover positive direction, v direction coverage will try to do it in negative direction. Okay, all of this velocity integrated over time, right? Integrated over time, that means 0 to whatever t that we wrote even in the upper this thing, should result in only x direction displacement. So if a particle starts here and reaches here, what is the x displacement? I think bd. So I'll write this as that bd. Okay, so this is my second analysis. Okay, so these are the two, and always we need two analysis to eliminate this sine theta dt terms. Okay, so let me write this one again. This would be simply u capital T minus that v comes out please, and that integral that you have above and below sine theta t 0 to t should be your bd. Okay, right. So I would love to eliminate this part and this part. So how do I do that? I'll bring all of that part only onto one side and say that this and this together will imply, okay, what will it imply? What about the left hand side of this? This is AC minus DC, right? This is AC minus DC. Okay, so I'll just write I'll substitute this one's function in this one. Okay, so on the left hand side of the one, AC minus DC is equal to VT minus U times of U minus U times of, I'll substitute this function here. The value of this integral integral sine theta theta will be ut minus bd divided by v. So I'll just write this is equal to ut minus bd divided by v. So this is your substitution. Okay. So let me look at what he wanted. He wanted AB and BD's relation. Okay. So DC, whatever is there, the DC, I'll split it up in BC and BD. Everything I want finally only in terms of AB. Okay, everything in terms of AB. So if AB is D and BC is 3D by 4, BD is extra. Okay, so it's very difficult dragging it every time. So I will just redraw that. A, B, C, and D. I think this was D. This was 5D by 4. This was 3D by 4. Okay, this will give me a pretty picture, easy for you to also follow it. The value of AC, I'll just substitute 5D by 4 that I already know, minus DC, I'll write it as BD that I don't know, plus 3D by 4 on the left hand side is equal to VT minus I think this value would be VT minus U times of Anyway, V is equal to U was given, I guess, right? V is equal to U I have not yet substituted, so I'll just take care of that. So this would be, in the next step I'll do U square T by V minus U BD divided by V. So all these V's will get cancelled anyway. So this entire thing would be U of that number this and this is getting cancelled, and this would be 2D by 4 minus BD is equal to, I think this entire thing will get cancelled. I think I made a mistake with BD or something like that. So DC, AC and DC, if I subtract, DC is BD plus BC, okay? And that I wrote it correctly. Here minus of minus I made an error. Can you carefully observe? This one, minus of minus, right? Minus of minus, I think I messed it up here. This is plus. Now I think I'm fine. So this would be again a BD on this one. So this implies 2BD, or simply BD is equal to D by 4. Okay, BD is equal to D by 4, which tells you the original expression, that is how much AB by BD. AB by BD should be equal to 4. So this is your answer. I took D as AB, right? So I just substituted that one. I know it was a bit tedious, but the whole idea was to be able to do these two analysis. Always try to look at what is the way to eliminate this unknown kind of integral. This you can't integrate, so that's why we write it twice in two different forms. One is the vector equation, another is the separation equation. Always these kind of questions of chasing will involve these two. Okay, so that's what we did. Rest of the manipulation and all depends. You could see pretty weak in my calculations and all that, so that's why I take a bit of time. You people are much sharper than me, so you should be able to go ahead with this. So my job is to more of teach this part. Okay, I think I did pretty well anyways here also. This is 4 is the final answer. Okay, let's move on. Another one. This time let's see two ships moving. Two ships moving on a calm sea. Moving on a calm sea, with ship A moves towards northeast. Ship A moves towards northeast. First ship moves towards northeast at 16√2 kmph. Okay, and ship B moves towards, he will say due north. Due north means moving towards north at 4 kmph. At 4 kmph at midnight. Midnight means 12 or 00 hours as they call it. Midnight. The ship B is 80 kilometers east of ship A. Ship B is 80 kilometers east of ship A. So that is a position of one with respect to other. They can communicate with each other. They can communicate with each other if the distance between them is less than or equal to 50 kilometers. So if they're farther away from each other by 50 kilometers, they can't send signals to each other. Okay, so they can communicate. So when this is happening, you need to find out 3 important aspects. This is a very important phrase they'll use in problems of relative motion. Least distance of approach. Least distance of approach of the two ships. That means how close they will come during their motion. Second one, at what time on clock do they start communicating? At what time on clock do they start communicating? Okay, right. Last one. For how much time period or how much period, similarly, do they communicate with each other? With each other. Okay, right. So these are the 3 questions. So at times they will mention everything in language and you're supposed to draw your own diagram. So this is that kind of a model. I repeat, the word midnight means 00 hours. So here maybe he's asking it whether it is 1 a.m., 2 a.m., 3 a.m. like that. That's the expectation. Okay. Right. So we'll try to do it in a diagrammatic approach. Let's say this is your north, east, west, south plane. So this is your horizontal plane, remember, right, that we are dealing with. So this is your north, this is east, this is south, and this is west. Okay. He said already that A, right, I'll directly go to this statement first. This one. Can you see? This one I'll draw at 12 noon. So how the positions are. He said, who is east of who? I think ship B is to the east of ship A. So for my convenience, I'll take ship A as origin and then mark ship B. So maybe I would say that this is ship A, and at this point, this is ship B, and AB length initially in my picture here should be 80 kilometers. So that's my understanding of how the problem is worded. Next important thing, ship A, while being at the position in the diagram, continues to move at 16 root 2 kmph in northeast direction. What is meant by northeast? That 45-degree line. So I'll just mark that arrow. So the ship A's vector of motion is this way. Okay, this is all based on ground observer. On the side, I will try to draw a relative frame. Don't worry about that. And at the same instant, ship B is moving with 4 kmph due north. Due north means towards north. Okay, 4 kmph. So I'll mark that with a different color. So maybe ship B, I'll mark a blue vector like this. So these are the informations given. So the yellow one is 16 root 2 in kmph. The blue one is the 4, very slow one, not drawn to scale. So with this, I will enlarge this diagram and I'll try to draw one ship with respect to another. So in my next diagram, let me demarcate this one off so that we are in a separate frame of reference. This new diagram I am drawing with respect to A. So I'm assuming ship A stays at where it is. Okay, right. So I'll try to enlarge this diagram. So this is your A. This is the so-called B. Okay, we can do one more thing actually. With respect to A, I said, so what I should do is I should reverse the velocity of A and add it to B like this, right? So maybe I need to draw this diagram a bit up than what it should be. So I'll try to borrow some more space so that I can illustrate that. So I'm saying this is the position A, this is your position B. Okay. Now with respect to A, velocity of B on the sideline, so velocity of B with respect to A is equal to velocity of B minus velocity of A, all bars obviously on the top, and which always also equal to velocity of B bar plus negative vector of A bar. Can I say that? So as seen by an observer sitting on A, so this is my observer now, he will say I am always at rest. Then he says I see a velocity vector of B and negative vector of A added to this B. So negative vector of A would be a reverse like this, right? That vector I'll place it here like this. Okay, so maybe I'll respect that 16 root 2 a bit more and draw it a bit longer like this. Okay, right, so this is your 16 root 2. So what will be the result of this blue and yellow vectors? I would say there is a 16 this way and there is a 16 this way fighting with that 4. Okay, so maybe in dotted form I'll write this is a 16 and this is a 16. So these two 16s, when they fight with 4, it results in a diagram. So I'll repeat drawing this diagram again down so that it's more clearer. So this diagram implies A still staying at rest because the observer is placed on A, and the B will have a resultant velocity of, listen carefully everyone, 16, that is there. Can you see 16 and 4 will fight and result in a 12 this way, right? There will be a 12 in the downward direction like this. 16 will be alone like this. So the resultant relative velocity of B as seen by A would be due to a 16 this way minus 12, which is 16 minus 4, which is a 12, and there is a 16 this way. There will be 16 this way. So the resultant motion would be a vector sum of this 16 and a 12, which would be a red line drawn like this. So this would be the direction of the resultant. So the motion of B with respect to A will be along this line. I think you can easily find out this angle theta. Value of the theta on the sideline I'll write is tan inverse of 12 by 16, which is 37 degrees. So you know that triangle. So A thinks A is at rest and B is moving along this red line. Remember, the actual motion won't be along red line. And one more very important thing, don't confuse yourself. This red line is not parallel to this yellow line. It's the line which is resultant of this yellow and this blue, which is somewhere here like this. So to find that red line, I use component form of addition. I did the component form, which is done over. So what is the least distance of approach? Least distance of approach is a frame independent quantity. In any frame, distance is always the same. It is the displacement that could be different, but the gap between the 2 points is always a frame independent quantity. So simply I'll draw a perpendicular from A onto the line observed to the B. So this would be the least distance of approach. So that LD, least distance of approach, if I write LD, least distance of approach, would be simply, if I finish this triangle for my convenience, can you see I finished it, the dotted line? Okay, right. What was this gap initially? The AB gap that you had, this entire gap. Please don't confuse yourself with that velocity. 16 was a kmph. This was a kmph. So it has nothing to do with 80 kilometer that you had. So this was 80 kilometer. And can you see that LD therefore in my diagram, least distance of approach, that's the first question, should be 80 kilometer multiplied by sine theta, right? Sine 37 degrees. Okay, so sine theta is 3 by 5 and you end up having 48 kilometers. So 48 kilometers, right? Now, second part of the question is very simple. If the least distance is 48 kilometers, which is this way, on either side of this line, there will be a 50 kilometer line that I can draw. Okay, so I'll draw those two lines, yellow in color. So maybe this is a 50 kilometer line on this side, and it symmetrically on another side of this line, there would be a 50 kilometer line. Okay, so just to ensure that my LD doesn't get covered up, I'll erase this and write it in a slant form so that you don't have a trouble visualizing. So this is blue one was my LD that I'm not disturbing, and I'm drawing a new yellow line on either side of a 48 kilometer line. If blue one is 48, I can always find two yellow lines on either side, which is 50 kilometers in length. So this is what I'm claiming is 50 kilometer in yellow. So which means from a point here, which is let's say P, and from a point here Q, for this length PQ, I think the ships will be in communication, because any position between P and Q, the distance will be less than 50 kilometer, which was responsible for the communication in the question. Okay, right? So they will start communicating at P and they will stop communicating at Q. They'll start communicating at P and they'll stop. So what was the question? Let me read it back. At what time on the clock they will start communicating? That is that time when in this diagram the ship B moves from B to P. This length I want to calculate. This length. Okay. So for that, again, I'll draw a part of the diagram. Yellow line borrowed, red line borrowed, and that white 80 kilometer drawn as it is. Okay, so this was 80 kilometer, this was your A, this was your B, this is your theta, and this yellow one was 50 kilometer. Okay, so I think I can find this red colored using cosine rule, right? Or is there any other way of looking at that? I think I can use sine rule also, because if we are smart enough, which we are, if this is 50 and this is 48, you can get this angle. That means you know this angle. Since this angle and this angle are known, with this side and this side known, you should be able to get this side. Okay, so if I get that particular value, let me mark this position easier for me. This is R. BR square, can you see in that original triangle, should be AB square minus AR square. So the value of BR would be square root of AB, which is 80 kilometer square minus 48 kilometer square. So you can find the value of BR. Once BR is known, we can also note PR value is equal to root of 50 kilometer square minus 48 kilometer square. I took two right angle triangles. Can you see one big right angle triangle here to avoid sine rule cos rule? You can go ahead with sine rule cos rule here, but I'm trying to do it a bit differently. Okay, so this big right angle triangle, can you follow the diagram? Big right angle triangle, right? I found BR square is equal to 80 square minus 48 square. Then there is a shorter right angle triangle like this, where 50 square minus 48 square will give you. So with BR known and PR known, I can find BP. So the value of BP is equal to PR minus PR. You'll get some number, right? And with that number, you would say the time duration after which the communication starts would be to travel BP, right? BP distance has to be traveled with the speed of the resultant velocity. What was the resultant? The 16 and 12 resultant in this direction you have to write. So which is simply root of 16 square plus 12 square. Okay, you can do these calculations, not very tough, but we are running out of time, so I've done it on the sidelines. You end up getting this as 2.5 hours. Since it is after 00, on clock it will show 2:30 a.m. So at 2:30 a.m. they will start communicating. And for how much time they will communicate? The delta T of communication should be when it travels what distance? I think PQ distance. During PQ, it will be able to communicate. So delta is PQ length divided by, again, the same speed with which it keeps moving. This one would come out to be 1.4 hour. Trust me, I've done these calculations on the sidelines, so I'm writing them directly. You should be able to do this. So if in minutes it is asked, 1.4 hours is 84 minutes you would get. So these are the So I drawn this, but I didn't use it, by the way. So this triangle would have been for sine or cos rule, which I didn't use. So this one I didn't use. I tried doing it in a different manner using right angle triangles. It may not be the best method. It's just that whatever stuck me, I did that. So that's it. These are the three questions that we tried to answer. Okay. So this was more of a pictorial way of solving the same question by using with respect to, so you people could have used with respect to B also. You sit on B, then reverse the vector of B and add it to A, then A will travel accordingly, but you'll get a similar triangle in a different orientation. So distances won't change. So maybe you could have chosen with respect to P also. The whole idea is sit on one ship, watch the other. That's the best way of solving. Okay, right. So that finishes our class today. We'll continue with the miscellaneous problem whenever we get time. So tomorrow it will be more of the DPP doubts clarification, and we'll continue with the miscellaneous. I still have many more models to cover in kinematics. So the next week, whenever we meet, if at all we meet, we'll definitely cover and continue from where I left. It's not at all over. We have to do a bit more in this particular topic. Okay, right.